Okay, so we have talked about accuracy of a regression model, and we have proved that with respect to the mean squared error, the best possible model is the expected value of y given the observed value of x. Now let us talk about accuracy of a classification model. So recall that the output of a classification model is a probability vector. So it's just not just a label, but it is the whole vector. So in this case, so notice that the highest probability class is always no. So which means that in this case, our model always predicts no. But the observed output is 4 no's and 1 yes. Now, here is the definition of the overall error rate. So what is it? What does it mean? So this I here is the indicator function. So the indicator function is basically 0 or 1. So it is 1 if the condition is true. So if yi does not equal to yi hat, and 0 if the condition is false. So if yi equals to yi hat. Right? So if the observed value is the same as the predicted value, it contributes 0 to the sum. If the observed value is different from the predicted value, it contributes 1. In this case, observation 1, the observed value is no, the predicted value is highest probability is also no. So 0, 0, 0, 0, 1. Right? So it means that in this case, this sum is going to be 1. But since this is just the sum of zeros and ones, it is quite clear that what we see here is just 1 over n. So, and n is the total number of our observations times the number of incorrectly classified observations. So, misclassified observations. So this is just 1 over n times the number of misclassified observations. That's what it is. So here is a simple example. Confusion. Yeah, by the way, usually for classification problems, we print the so-called confusion matrix. Right? So for confusion matrix, we list all possible values, arrange them in a table. So rows of this table represent predicted values, columns represent actual values, observed values. So reference here means observed values. Right? So in particular, I don't know, this number 782 means that this is the number of cases where we predicted no, but the actual value is yes. Right? So then the error rate is just the number of observations that are off the main diagonal in this matrix. So if this is a bigger matrix, then whatever goes along the main diagonal are correctly classified observations. So whatever is off the main diagonal is incorrectly classified observations. Right? So the error rate is therefore the number of the total sum of entries of the confusion matrix on off diagonal divided by the total sum of entries. So this is the overall error rate. Now the problem with this error rate is that it's not sensitive to small changes in probability. It does not rely on probabilities at all, right? So, which means that if we have two models with the that produce the same predictions, but one model is 99% confident and the other model is only 60% confident, the overall error rate is going to be the same, right? But of course, we want to pick the model that is more confident, right? So from this point of view, it is better to somehow assign an error rate in a way that takes account these confidence levels. And here is our credit card default example. And so basically the idea here is that, okay, so one observation here is misclassified. But at the same time, notice that the probability of the no prediction here is the lowest out of all. And the idea here is that we should penalize those models that are not too confident in their incorrect predictions. Not too much. That's the idea. So, and this is done by the so-called cross-entropy error function. Yeah. In the next lecture, we will see kind of more motivation behind this cross-entropy. But now let me just explain what it means, right? So this is the sum over all observations and over all possible values of the categorical variable. Right? So the sum. So this is the sum of all observations, and this is the sum of all categories. But notice that the first multiplier here is yik, but yik can be either 0 or 1. So this is yik. So this is yik. And of course, if yik is 0, well, it doesn't contribute anything to this cross-entropy rate. So it means that we should only take the sum over all categories in which the value in the so the entry of the outcome is 1 and not 0, right? So we should take this, and this. Okay, so what does it look, right? So it means that the corresponding y hat is the probability is going to be this number, this number, this number, this number, and this number, right? So in this case, this is going to be the sum of minus log of this 0. The first is 0.80. Let me round it to 2 decimal places. So 86 minus log. The second one is 0.89 minus log 0.84 minus log 0.91 and minus, so let me continue here, minus log of 0.22. Right, so the numbers here are between 0 and 1. They're always probabilities. So which means that the log of this number, logarithm, is negative. So minus logarithm is going to be positive. And the closer this number to 1, which means the more confident the model is, the smaller the number is going to be, right? Because logarithm of 1 is 0. And logarithm of a number that is very close to 0, something like 0.0001, is going to be a large number. So this is big. But logarithm of, say, 0.99 is almost 0. Which is why it kind of captures this cross-entropy function. It captures this idea that models that are more confident in their predictions should have a lower error rate, or a lower cross-entropy, right? So lower deviation from the ideal. And of course, the ideal situation would be if these are just all ones, and this is also 1. So in that case, the entropy is going to be 0. Okay, so here is a little quiz about error rate and cross-entropy for you.